Welcome to this coding problem walkthrough. Today, we'll explore problem number 1043, titled Partition Array for Maximum Sum. In this session, we'll break down the problem, discuss the underlying concepts, and go step by step through the solution approaches. Let's dive in. In this problem, we are tasked with partitioning an integer array called ARR into several contiguous subarrays. Each subarray must have a length that is at most k. Once we've partitioned the array, every element in each subarray is replaced by the maximum value of that subarray. The goal is to determine the largest possible sum of the modified array after this process. For the input format, we are given two parameters, ARR, which is a list of integers with a length between 1 and 500, where each element is non-negative and can go up to 1 billion, and k, which is an integer between 1 and the length of the array. The output is a single integer representing the largest sum of the modified array after partitioning. Let's look at some examples to better understand this problem. In the first example, we are given the array ARR equals 1, 15, 7, 9, 2, 5, 10, and k equals 3. The output for this input is 84. Here's how we arrive at that result. The array is partitioned into three subarrays, 15, 15, 15, 9, 9, and 10. Notice that in each subarray, all elements have been replaced by the maximum value of that subarray. Summing these values gives us 15 plus 15 plus 15 plus 9 plus 9 plus 10 equals 84. Another example is ARR equals 1, 4, 1, 5, 7, 3, 6, 1, 9, 9, 3, with k equals 4. Here, the output is 83. In this case, the array is partitioned into 4, 4, 5, 7, 7, 7, 7, 7, and 9, 9, 9. The sum of the modified array is 4 plus 4 plus 5 plus 7 plus 7 plus 7 plus 7 plus 9 plus 9 plus 9 equals 83. A simpler example is when ARR equals 1 and k equals 1. In this case, the output is 1. Since the array contains only one element and k is also 1, no partitioning is possible, so the sum remains the same as the only element in the array, which is 1. Now, let's consider the constraints of the problem. The array length is limited to a maximum of 500 elements, and each element is a non-negative integer that can be as large as 1 billion. Furthermore, the maximum size of a subarray, defined by k, is constrained to be between 1 and the length of the array. These constraints ensure that the problem remains computationally feasible while still allowing for a wide variety of input scenarios. There are several key edge cases to consider for this problem. First, if the array contains only a single element, such as ARR equals 5 and k equals 1, then no partitioning is possible, and the result is simply the value of the single element, which is 5. Second, when all elements in the array are the same, such as ARR equals 3, 3, 3, 3, with k equals 2, the result is the sum of all elements in the array since no matter how we partition them, the values remain unchanged. Third, when k equals the length of the array, the entire array can be treated as a single subarray, maximizing the sum by replacing all elements with the largest value in the array. Finally, when k equals 1, no partitioning is possible, and the sum is the sum of all elements in the array since each element becomes its own subarray. These examples highlight the importance of considering both the structure of the array and the value of k to find the optimal solution. To solve this problem, we first considered the brute force approach. The intuition here is to explore every possible way to partition the array into subarrays of length at most k. For each partition, we calculate the sum by replacing every element in a subarray with its maximum value, and then take the maximum sum across all these partitions. However, this approach has significant drawbacks. The number of partitions grows exponentially with increasing k, leading to extremely high time complexity. Additionally, many of these computations are redundant since overlapping subproblems are recalculated multiple times. This inefficiency makes the brute force method impractical for larger inputs. Next, we explore the dynamic programming approach, which offers a more structured and efficient solution. The key idea is to break the problem into smaller subproblems and use a bottom-up strategy to avoid redundant computations. We define dp, I, as the maximum sum achievable considering the first I elements of the array. For each index I, we examine all possible subarrays of length 1 to k that end at I. For a subarray of length j, its contribution to the sum is calculated by multiplying the maximum value in the subarray by j. Using this formulation, we derive the recurrence relation dp I equals max dp ij plus max error ij plus 1 I asterisk j for all valid values of j. This dynamic programming approach systematically builds solutions to larger subproblems by leveraging solutions to smaller ones, significantly improving efficiency compared to brute force. The dynamic programming approach has several key advantages. First, overlapping subproblems are solved only once, which drastically reduces redundant computations. This is the cornerstone of why dynamic programming is much faster than brute force. Second, efficiently finding the maximum value in a subarray is vital for performance. By carefully managing this computation, we can ensure the approach remains efficient. In terms of complexity, the time complexity is O, n asterisk k, where n is the size of the input array and k is the maximum length of the subarray. This is because we iterate through the array and consider up to k subarray lengths at each step. The space complexity is O, n, as we only need to maintain the dp array to store the solutions to subproblems. Additionally, there is an optimization using a sliding window or DEEC. This method dynamically tracks the maximum value in the current range, reducing the need to recalculate the maximum for overlapping subarrays. However, implementing this optimization adds complexity without significantly improving performance for standard constraints. As a result, while it is an interesting idea, it is generally unnecessary when the dynamic programming approach already achieves the desired efficiency. The dynamic programming approach provides a systematic way to compute the maximum sum by leveraging overlapping subproblems. By iterating over possible subarray lengths and efficiently tracking the running maximum, we achieve optimal performance without excessive memory usage. This balance of efficiency and simplicity is what makes the DP approach so effective. When comparing the different strategies, the brute force method, while simple to understand, is far too slow for larger input sizes due to its exponential time complexity. On the other hand, the sliding window optimization, while faster in certain scenarios, introduces significant implementation complexity and is not necessary given the constraints of this problem. Dynamic programming strikes the right balance, offering clarity, maintainability, and excellent performance. This approach ensures we achieve the desired result in O, n asterisk k, time using manageable space, making it well suited for competitive programming and real-world applications. By carefully structuring the solution, we can confidently handle larger inputs while maintaining both efficiency and readability in our implementation. To solve this problem, our goal is to partition the given array into subarrays of length at most k, replace all elements in each subarray with the maximum value of that subarray, and then compute the sum of all these transformed subarrays. The objective is to maximize the sum while adhering to the constraints on partitioning. To approach this, we use dynamic programming. We define dp I as the maximum sum achievable by partitioning the first I elements of the array. The base case is straightforward: if there are no elements, the sum is 0, so dp 0 equals 0. For the transition, we look at all possible subarrays ending at each index I. For a subarray of length j, the contribution to the sum is j multiplied by the maximum value of that subarray. By iterating over all valid subarray lengths, we can compute the optimal solution for each position in the array. The recurrence relation for this problem is expressed as dp I equals max dp ij plus j asterisk max underscore value, where j ranges from 1 to k, and we ensure that ij is non-negative. To efficiently compute this, we iterate backward over the last k elements or fewer if I is less than k. As we iterate, we dynamically calculate the maximum value in the current subarray to avoid redundant recalculations. Once we have processed all elements of the array, the result of the problem will be stored in dp n, where n is the length of the array. This approach ensures that we systematically account for all possible partitions and maximize the sum. There are a few key insights that optimize our approach. First, we can significantly reduce redundant calculations by maintaining the maximum value in a sliding window as we iterate backward for j equals 1 to k. This dynamic approach avoids recalculating the maximum for overlapping subarrays. Second, we need to consider edge cases such as when k is greater than the length of the array. In this situation, the entire array can be treated as one subarray. Similarly, if the array consists of identical elements, all partitions yield the same result, so the solution remains straightforward. For very small arrays, such as when the array has only one element, only one subarray is possible. Lastly, when analyzing complexity, the time complexity is O, n asterisk k, because for each index, we examine up to k previous elements. The space complexity is O, n, due to the DP array that stores results for each index. The implementation relies on two core data structures. First, the DP array, which stores the maximum sum obtainable up to each index, has a size of n plus 1 to accommodate the base case. Second, we use a variable to track the sliding window maximum dynamically as we iterate through potential subarray lengths. This prevents redundant calculations and keeps our algorithm efficient. To see how this works in practice, consider the example where ARR equals 1, 15, 7, 9, 2, 5, 10, and k equals 3. We initialize the DP array with all zeros, including an extra slot for the base case, so DP equals 0, 0, 0, 0, 0, 0, 0, 0. This setup provides the foundation for filling in the DP table based on our recurrence relation. Now, we populate the DP table step by step. For I equals 1, the only subarray is 1, so DP 1 equals max 0 plus 1 by 1 equals 1. For I equals 2, we consider 15 and 1, 15. The maximum value for 15 is 15, and for 1, 15, it's also 15. This gives DP 2 equals max 1 plus 1 by 15, 0 plus 2 by 15 equals 30. Next, for I equals 3, we evaluate 7, 15, 7, and 1, 15, 7. By calculating the respective sums, we find DP 3 equals max 30 plus 1 by 7, 1 plus 2 by 15, 0 plus 3 by 15 equals 45. Repeating this process for all indices, we eventually fill the DP table as 0, 1, 30, 45, 54, 63, 72, 84. The final result, stored in DP 7, is 84, which is the maximum sum achievable with the given constraints. The provided solution implements a dynamic programming approach to solve the problem of partitioning an array for maximum sum. Here's a detailed explanation of the code. 1. Initialization. The function maxsum after partitioning takes an array ARR and an integer k as inputs. The length of the array is stored in n, and a dynamic programming array DP of size n plus 1 is initialized with zeros. The DP array will store the maximum sum achievable for each subarray length. 2. Outer loop. The outer loop iterates through each index I from 1 to n. At each step, the algorithm calculates the maximum sum achievable for a subarray ending at index id1. 3. Inner loop. The inner loop considers all possible subarray lengths j from 1 to min, k, I, to ensure that partitions do not exceed the constraints. For each subarray length, the maximum element within the current partition is calculated and maintained in the variable current_max. For calculating maximum sum, for each partition length j, the algorithm updates the DP I value by comparing its current value with the sum of DP ij, the maximum sum achievable for the subarray before the current partition, and current_max asterisk j, the contribution of the current partition, where all elements are replaced by the maximum value. 5. Result. After the loop's complete, DP n contains the maximum sum achievable for the entire array. This solution efficiently calculates the result in O, n asterisk k, time complexity, where n is the length of the array and k is the maximum partition size. The space complexity is O, n, due to the DP array. This is the Java implementation of LeetCode problem number 1043, partition array for maximum sum. The logic mirrors the Python implementation, with differences in syntax and type declarations. The maxsum after partitioning method uses dynamic programming to calculate the maximum sum that can be obtained by partitioning the array into subarrays of size at most k. Key differences include the use of Java arrays and explicit loops for iteration. This implementation ensures clarity and efficiency while adhering to Java conventions. In this problem, the goal is to partition the array ARR into contiguous subarrays, with each subarray having a size of at most k. The objective is to maximize the sum of the maximum values in each subarray, where each maximum value is multiplied by the length of its respective subarray. We approach this problem using dynamic programming. Let's break it down with the first example, where R is 1, 15, 7, 9, 2, 5, 10, and K is 3. First, we initialize the length of the array as n equals 7 and prepare a DP array of size n plus 1, filled with zeros, to store the maximum sum achievable for the first I elements. The base case is DP 0 equals 0, representing no partitions. Now, we iterate over each index I from 1 to n. At I equals 1, we consider all possible partition sizes up to k or I, whichever is smaller. Here, the only possible partition is of size 1, so we calculate the maximum value in that partition, which is 1, and update DP 1 to 1. The updated DP array becomes 0, 1, 0, 0, 0, 0, 0, 0. Next, we move to I equals 2. Here, we examine partitions of size 1 and 2. For a partition of size 1, the maximum element is 15, so DP 2 becomes max 0 DP 1 plus 15 by 1, which evaluates to 16. For a partition of size 2, the maximum value across both elements is still 15, and we calculate DP 2 as max 16 DP 0 plus 15 by 2, which results in 30. At this point, the DP array is updated to 0, 1, 30, 0, 0, 0, 0, 0. Moving to I equals 3, we now consider partitions of size 1, 2, and 3. For size 1, the maximum value is 7, and DP 3 becomes 37. For size 2, the maximum between 7 and 15 is 15, and DP 3 remains 37. For size 3, the maximum across all three elements is 15, and DP 3 is updated to 45. The DP array is now 0, 1, 30, 45, 0, 0, 0, 0. This process continues until I equals 7, where we compute the optimal partitions for the entire array. By the end of all iterations, the final result is stored in DP 7, which equals 84. Let's look at another example where ARR is 14157361993 and K is 4. Here, the length of the array is n equals 11. And we initialize the DP array with zeros, of size n plus 1. Using the same dynamic programming approach, we calculate DP, I, for each index. For instance, at I equals 4, we can form a partition, 1415, which yields a DP, 4, value of 20. For I equals 8, one possible partition is 57361, leading to a DP, 8, value of 54. After processing all elements, the final value DP, 11, is 83. Similarly, consider a smaller example where ARR is 10, 20, 30, and K is 2. Here, the partitions are straightforward due to the size of the array. For I equals 1, the maximum sum is 10. For I equals 2, the partition 10, 20 gives a maximum sum of 40. Finally, for I equals 3, the partition 20, 30 results in a sum of 60. Thus, the output for this example is 60. To better understand this approach, let's visualize how the DP array works. At each index I, DP, I, stores the maximum sum achievable by partitioning the first I elements of the array. The inner loop iterates over possible partition sizes, and for each size, it computes the maximum value in the current partition, denoted as current_max. This value is then used to update DP, I, ensuring that all subproblems are solved optimally. The time complexity of this solution is O, n asterisk k, where n is the length of the array and k is the maximum partition size. This is because for each I, we iterate over up to k partition sizes. The space complexity is O, n, as we only store the DP array. This efficient use of dynamic programming allows us to solve the problem within the given constraints. To analyze the time complexity of this solution, let's look at the different components. First, the outer loop iterates through the indices of the input array from 1 to n plus 1. Since this loop executes once for every index, it contributes O, n, iterations, where n is the length of the array. Next, for each index I, the inner loop iterates over j, which ranges from 1 to min, k, I, plus 1. In the worst-case scenario, when I is greater than or equal to k, this inner loop runs O, k, times. Because the inner loop is nested within the outer loop, the total contribution from these nested loops becomes O, n asterisk k. Lastly, the computation of the maximum value in the statement current_max equals max, current_max, or ij, is a simple comparison operation between two values, which takes constant time O1. This means it doesn't impact the overall complexity. Combining these factors, the total time complexity of the solution is O(n*k). Now, let's analyze the space complexity. The primary data structure used here is the dynamic programming array, dp, which has a size of n+1. This contributes O(n) to the space complexity. Additionally, the variables current_max, I, and j only require constant space, or O1. Since no other data structures are involved, the overall space complexity is O(n). Moving on to the best, average, and worst-case scenarios, the algorithm consistently evaluates all possible partition sizes up to k for every index I. This means that in all cases, whether best, average, or worst, the time complexity remains O(n*k). The worst-case scenario occurs when k is large, approaching the size of n, as this maximizes the number of iterations in the inner loop. Comparing this optimized dynamic programming approach to a brute force solution highlights its efficiency. A naive method would involve generating all possible partitions of the array and calculating the sum for each, which results in exponential time complexity, O(2 to the power of n), due to the sheer number of possible partitions. In contrast, the dynamic programming approach reduces this to O(n*k) by leveraging previously computed results and restricting the partition size to k, which is a significant improvement. Mathematically, this complexity arises because the outer loop runs n times, and for each iteration, the inner loop runs at most k times, resulting in O(n*k) operations overall. The space complexity, on the other hand, is primarily determined by the dp array, which is of size O(n). Since no additional large data structures are used, the overall space complexity remains O(n). When solving this problem, there are a few common mistakes to watch out for. First, neglecting to handle edge cases can cause significant issues. For example, when k equals 1, every element becomes its own subarray, which simplifies the problem but needs to be explicitly handled in your logic. Similarly, when k equals the size of the array, n, the entire array becomes a single subarray. If these boundary cases are not considered, your solution might fail or produce runtime errors. Another common pitfall is overlapping subarray calculations in dynamic programming approaches. Without proper memoization, you could end up recalculating the same subarray sums multiple times, which is highly inefficient and can cause time limit errors. Index out-of-bounds errors are another frequent issue, especially when iterating over subarrays of length k. It's easy to accidentally access indices beyond the array length or use incorrect ranges in your loops. Lastly, using a naive approach to find the maximum element within a window can hurt performance. For example, recalculating the maximum for each sliding window in k time instead of leveraging a more efficient data structure like a deque or a heap can make your solution much slower, especially for larger inputs. Also, it's important to keep an eye on time complexity constraints during optimization. While some approaches may seem correct, they might exceed the allowed time limits for larger inputs. For instance, when k is very large, like 10,000, and the array size is 100,000, brute force methods will not suffice, and you'll need to ensure your solution runs in O(n) or O(n log k) time. From an interview perspective, pattern recognition is key. This problem falls into the classic max and subarray category, which can be approached using dynamic programming, sliding windows, or monotonic queues. Recognizing these patterns quickly can help you determine the optimal solution. It's also critical to understand trade-offs. While brute force methods may work for small constraints, they won't scale for larger test cases. Be prepared to analyze time complexity and explain why your optimizations are necessary. Communication is another crucial skill. Always clarify constraints and edge cases with your interviewer to demonstrate that you're thinking critically about the problem's boundaries. Finally, some problem variations may require optimizing for space usage. You should be ready to discuss whether your solution uses O(n) or O(1) additional space and why that choice is appropriate. There are several related problems that can help deepen your understanding of the concepts behind this one. For instance, LeetCode 239, sliding window maximum, demonstrates how to use a DEEC to efficiently find the maximum in a sliding window. LeetCode 53, Maximum Subarray, introduces the idea of summing subarrays, but in a simpler context. LeetCode 1231, Divide Chocolate, applies a similar partitioning strategy, but with the goal of maximizing the minimum sum, adding a twist to the logic. Another related problem, LeetCode 410, Split Array Largest Sum, involves partitioning an array to minimize the largest partition sum, which can be tackled using binary search and dynamic programming. As for alternative approaches, dynamic programming strikes a balance between time and space complexity, but you'll need to carefully manage state transitions to ensure correctness. Its time complexity can range from n*k to better, depending on how well you optimize. The sliding window technique paired with a DEEC is another approach, offering exceptional time efficiency at n. However, it can be more challenging to implement and debug, so it's best suited for situations where you need frequent maximum updates within a fixed length window. Another variation worth exploring is the combination of binary search with a greedy strategy. This method is particularly useful for problems that require minimizing the largest partition sum, as seen in some extensions of this problem. The trade-off here is that while this approach can be very efficient, it may not always be directly applicable depending on the specific constraints or requirements of the problem. In terms of complexity, it typically runs in n-log, max_sum, where max_sum represents the largest possible subarray sum. This makes it a powerful tool for tackling partitioning problems that involve optimization criteria, though it requires careful implementation to ensure both correctness and efficiency. Great job following along. We tackled problem number 1043, Partition Array for Maximum Sum, using a dynamic programming approach. Remember the importance of breaking problems into smaller subproblems and leveraging constraints to optimize your solution. Don't forget to like and subscribe for more tutorials. Keep coding and see you in the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!